Hi Year 13. This video is going to start you off on the integration chapter, which is obviously following on from differentiation. So a lot of it's going to be reversing the techniques that we learned in the differentiation chapter. I will advise you though that integration is considerably harder than differentiation in that the techniques that we're going to learn aren't quite as precise as they've been for differentiation. Okay, so when we did differentiation, we learned 3 rules basically, and using those rules or combinations of them, you can pretty much differentiate anything that's given to you. But for integration, it takes a lot more intuition and a bit more educated guesswork in order to get the answer to fall out. Okay, so we're going to go through a reasonably steady pace. Today is just going to be to do with integrating standard functions, as you can see on the top. So all the functions that we differentiated before, we're just going to write down them integrating back again. Okay, so you're going to want to copy this table down. On the left, we've got some standard functions, and on the right, we're going to have their antiderivatives. Remember the notation from year 12, we've got the integral symbol and then the function, and then we're integrating with respect to x, that's the dx part. Okay, so the first row of this table then is integrating a polynomial, x to the n, and this is just stuff that you've done in year 12. And if you remember, to integrate an x to the n, you raise the power up by 1, and then you divide by that new power, so that's the 1 over n plus 1. And then don't forget there's a constant of integration as well. And that's because, if you remember rightly, if you differentiate a constant, that becomes 0. So in fact, you get a family of solutions with any constant on the end rather than just the thing itself. Okay. So don't forget that. Perfect. Okay, so e to the x, some of the new ones then. Well, we know that e to the x is its own derivative. So if you reverse that back again, that's going to be e to the x again. So just e to the x plus c when you integrate. Right, 1 over x. 1 over x is a tricky one because it's a special case of this top one, x to the n, and 1 over x is x to the minus 1. But if you try and use this rule to integrate 1 over x, you're going to have a problem because 1 over minus 1 plus 1 is 1 over 0, which you can't do. But if you remember from lessons that we've done with differentiation, there is a function that differentiates to 1 over x, and that's the natural log. Now, that's what's underneath here, except you've got natural log of the absolute value of x. Okay, this is quite a small point, but it's not an insignificant one. So we need to take the absolute value of x, because if x is negative, then we can't have a negative inside our ln. So this absolute value guarantees that the argument is non-negative. Okay, so what we can also check is that if x is negative, then we can still check that ln of minus x, which makes it positive, is also going to be 1 over x. So d by dx of ln of minus x, where x is negative, makes this into a positive number, but then differentiating it with the chain rule gives you 1 over minus x, and then the inner derivative is minus 1, which cancels the minuses together, making it into 1 over x again. Okay, so that deals with both of those cases and stops this problem of x being negative. Okay, right, for the trig functions, we need to firstly remember the cycle of 4 that we had with sine and cos. So I'm going to draw that for you again. So sine of x, this is differentiating round clockwise, differentiates to cos of x. And then cos of x differentiates to minus sine of x, which differentiates to minus cos of x, and then back to the beginning again. Okay, so if we're integrating then, you've got to remember to go around this cycle the wrong way. Okay, we're going against the arrows to integrate. So that means cos of x is going to integrate to sine of x. Okay, sine of x integrates back round to minus cos of x. Right, the bottom 4, we have found those as derivatives of the other trig functions that we've come across. An important one to remember is definitely this one, sec squared of x integrates to tan of x, because when we differentiated tan, it made a sec squared. Cosec cot looks a lot like the derivative of cosec of x, except cosec of x differentiated to minus cosec cot. So when you integrate, this is going to go back to minus cosec of x. Okay, Cosec squared is almost the derivative of cot of x, except cot of x went to minus cosec squared. So this needs to be minus as well, again with plus c. And then sec x tan x is the exact derivative of sec of x. Okay, so fill in the grid. Keep this handy because when we come across these functions, we're not going to do much manipulation of these just yet. We're going to keep them pretty much as they are. You know what their antiderivatives are. Okay, right, so before we move on to any proper questions, the next slides on this PowerPoint that I'm going to attach to you, I've just got some quickfire ones. So you can try and commit these to memory straight away. That's probably a good thing to do. And you can test yourselves on these by uncovering them as you kind of go through. So this slide here, you can test yourself mentally and you can have a go and check. Same for these ones. And then there's some more there as well. Okay, just get the hang of using those antiderivatives. Right, some proper questions then. So you're going to get combinations of these things, and then at some point we're going to be involving the reverse product chain and quotient rule, but we haven't quite got there just yet. We're just sticking to some easy ones. Before we kind of have a stab at these, it's worth noting down 2 facts about integration that you could remember from last year. So firstly, if you're looking at sums of things, you can split that up into separate sums. So if I'm integrating 2 cos x plus 3 over x minus root x, you can integrate them separately. So that's worth writing down. So integrating some function plus another function, dx. Well, we don't need to write it particularly in a question, but we can split it into 2 separate integrals. That's integrate f of x dx plus integrate g of x dx. Okay, so that's something that you probably do mentally, but it's worth knowing that that's something that you're allowed to do. And secondly, if there's a constant in your integrand, the thing that you're integrating, then you can factor that out. And that's quite a useful technique, particularly when we get to the more difficult integration methods. So we've also got integrating a constant multiple of f of x means that we can factor this constant out. So the k is going to come to the front, and then you just integrate the bit that's left over. Okay, right, those rules can be written down and put to one side. So now that means we can do this top one. So integrate this stuff that I've said before. Before you integrate, the one thing that I can spot is that I want to turn this into an x to the power of something, because that means I can then integrate it. Root x is, well, I'm going to put the minus on as well. Minus x to the half makes minus root x. And then everything's of a form that I can integrate. So term at a time, 2 cos of x. The 2 is going to stay at the front, as we've got for this rule down here. Cos x integrates the sine of x. 3 over x, you can think of as 3 lots of 1 over x. And 1 over x went to ln. So this is going to give us 3 lots of the natural log of the absolute value of x. Okay, I'm going to probably begin by putting these absolute value bars on, but mark schemes don't tend to penalise you if you don't put these bars on. Okay, so I might end up being lazy and take them off. So we'll see what I do. So that's that, and then the third term, minus x to the half. You can look back at the table. It goes to x to the n plus 1. So the half will go up to 3 halves, and then you're going to divide by 3 halves, but dividing by 3 halves, you can flip and times, so that's timesing by 2/3. Okay, that saves me that tidying up step. Okay, and then don't forget plus c as well, and that's finished. Okay, if you want to check your answer, it's normally easier to check your answer by differentiating. So just as a double check, sine differentiates the cos, yes, ln goes to 1 over x, yes, and then this part, these times together to make a 1, and then that goes back down to a half, so we're good. Right, secondly, we've got integrate cos x over sine squared x. Now, you might be tempted to kind of reach for a quotient rule here, but we don't really have an integration for a quotient rule just yet. But what we can do is we can do some simplifying, or some we can rewrite this in a way that makes it obvious how to integrate. So let's think about what we can split this into. So cos of x over sine squared, I can write that as cos x over sine x, which gives me a certain trig function. And then that's times by, we need to get another sine x, so it's 1 over sine x on the bottom as well. dx. Okay, so that's split up into two separate bits. Each has its own name, and then when we put them together, we can see what it integrates to. Cos over sine x is cot x. 1 over sine x is cosec x. And from our list of derivatives on the previous couple of slides, that integrates nicely. That goes to minus cosec x plus c. Okay, so again, one of the standard ones in disguise. All right, thirdly, we've got this one at the bottom with unknown bounds on. Now, it's been a while since we've done any of these. Remember, when you stick bounds on your integration symbol, that's telling you to find an area between these two values. So as a little diagram of what we're trying to achieve here, so our function is 2x plus 1 over x, which I'm just going to draw like that. And we're integrating from a to 3a. And it's telling us that that area is given as ln of 12. So all of this stuff here, in between the bounds, is ln of 12. Okay, and we're after the value of a. Okay, so if you remember, if to figure out an area, which is called definite integration, as opposed to indefinite integration. So what you do is, if you're integrating from a to b of some function f of x, then you integrate this function f of x, and that becomes big F of x, and then you plug in the upper bound first, which is b, and then you subtract it from f of little a. Okay, so that's quite important. That's what we covered last year. That's just a little reminder of what to do. Okay, so if you want to get that down, you can pause the video and then draw that in. Okay, right, let's carry on with this one and get it done properly. Now, the hint in the box is telling us what to do with this fraction. So we like to have split numerators, because split numerators allow us to split our fractions into two separate pieces, and it looks like that's going to be useful to us. Just be careful though, because a split denominator doesn't do the same thing. Yeah, that's a kind of thing that you should know as well. So you can't split like that. All right, let's integrate then. Integrate a to 3a. Split it up, you're going to get 2x over x plus 1 over x dx. Tidy up. So a to 3a, this is just 2 plus 1 over x. Make that better. Okay, right, 2 is a standard integral, that's just a constant. That's going to become 2 lots of x. That's still using the x to the n rule, except the power of 0. Then 1 over x, we now know goes to ln of x. I'm going to not put the bars this time because I don't need them. 3a. That's notation, remember, we put the upper bound on top and bottom, lower one on the bottom, sub them in, and then we know it also equates to ln of 12. Okay, so let's see what we get on the left side. We get, right, 2 times 3a is 6a. We get ln of 3a, and that's everything in with 3a, and then you subtract, and then you stick a in, you get 2a, and then you get plus ln of a, and that equals ln of 12. So that equals off. Okay, what does that give us? So now we've got 4a plus ln of 3a minus ln of a equals ln of 12. Okay. Now you might get stuck if you're not confident with logs, but remember we've got a log rule that can combine logs together when they're subtracted. And what's going to happen there is we can put that into a single one and divide the arguments. So now I'm going to move over to here. I'm going to maybe cover over this box. Right, so now what we've got is 4a plus ln of, and then these bits divide, 3a over a equals ln of 12. Then a's cancel out, so that just leaves ln of 3. Then I want to isolate a, so I'm going to move the ln to the other side. Minus ln of 3. But then again, we've got another log subtraction, so that's going to combine into log of 4. Okay, and then last step is to divide by 4. Oh. And then of 4. Okay, so that's sorted out. That is a perfectly decent answer, except what we can do is, because a quarter as a power agrees with 4 quite nicely, we can put a quarter as a power of 4, because that's another log rule. So that's log of 4 to the power of a quarter, and 4 to the quarter is root 2. Okay, so that's an alternate form for writing that down. Okay, right, that should be enough to kind of get you started as to how we're trying to solve these integrals. So for your lesson today, we're going to start with 11a is the exercise, and you're pretty much free to pick what you want to practice. And I think a lot of further maths students will have done a lot of this already, so you want to kind of pick some of the harder stuff. If I can actually find what I'm trying to do today. Okay, all right, 11a. So we've got a bunch of integrals here. What you might want to do is just choose a selection of each question, because there's quite a lot there. So I would suggest maybe 5 of these first 2. Maybe let's do alternating ones like that. That's probably a good selection. Don't have to do those ones, just pick until you've kind of got the hang of it, and then same for these ones. Okay, and then it's up to you to pretty much pick. So we've got them. And then I think the exam style ones are probably good ones to have a go at, particularly if you're further maths people. But it's up to you. As much as you can get done is pretty decent. Okay, right. Any problems then, please let me know. I'm happy to assist you with any of these and give you a bit of a hand. Otherwise, best of luck year 13, and I'll see you soon. I'll see you on Friday.